Assalamualaikum and hi everyone. First of all, I would like to thank my supervisor Dr. Wan Khairul Muzamil for helping and give me a lot of guidance in order for me to complete this study. So, let me introduce myself. My name is Sharifah Nur Nadiah binti YASSIN, and here I would like to present my Viva presentation with the title Aerodynamic Study of Symmetrical and Asymmetrical Airfoil in Varying Angle of Attack Airflows. So, the agenda for this presentation, I will explain about the introduction, objective, the problem statement, and followed by the literature review, the methodology, result and discussion, conclusion, and last but not least, the future recommendation. So, this study will be highlighted with three main things, which are renewable energy, aerodynamic, and airfoils. So this research mainly focus on three main objectives. So the first objective is to carry out a selection process of high lift to drag ratio airfoils based on the NACA 4 series using the Q-Blade software. So the second objective is to develop an experimental method of using a particle image velocimetry system integrated with various airfoils or known as a PIV system. And the third objective is to investigate the aerodynamic characteristic of symmetrical and asymmetrical airfoil blades in orthogonal fluid flow in the PIV system. So, move to the next agenda, which is the problem statement. As we know, renewable energy can play an important role by So by using the renewable energy, it can help to reduce environmental problems. And as I mentioned in this slide, the characteristic of wind in Malaysia have a low wind speed around 0.3 meter per second, and it often unreliable and unpredictable. So in this study, I have using two types of airfoils, which is symmetrical and asymmetrical airfoils. So both of these airfoils are being tested whether it can overcome the lift to drag problem in various angle of attack, or best to say, whether symmetrical or asymmetrical are the best to overcome the problem. So it is very important to have airfoil that have a high lift to drag ratio in order to overcome the lift to drag ratio problems. So next, I will move to the literature review. So the first airfoil shape pattern was registered under the name of Horatio F. Phillips. The figure that I put here, this is the Horatio F. Phillips, and a bit on the diagram that I put on this slide. So the design of the airfoil is dependent on aerodynamic characteristics. So as I mentioned previously, airfoils are divided into two categories, which is symmetrical and asymmetrical. So these aerodynamic characteristics are different depend on the airfoil speed, weight, and purpose. So symmetrical airfoils have identical upper and lower surfaces, resulting in no lift at zero angles of attack because the chord line and mean camber line are the same. So chord refers to the distance between the leading edge and the trailing edge, and the chord line is the straight line that runs from the leading edge to the trailing edge. So as I mentioned in this slide, the study are focused on using the NACA 4 series. So the first digit donates the maximum camber as a percent of the chord, and the second digit denotes the chordwise position of the maximum camber in tenths of the chords. The last two digits denotes the maximum thickness of the airfoil section as a percent of the chord. So, before I continue my presentation, I want to highlight that my focus area on this research is only to find out the airfoil shape that can be improved, that can be employed in the low wind speed environment. So move to the PIV system, or known as the particle image velocimetry. So it is an optical, non-invasive technique. So it is commonly used to visualize 3D flow fields, and it simultaneously measures the velocity field of an entire region within a flow. So a typical PIV setup include a high-speed camera, a high-power multipass laser, and an optical arrangement to convert laser output light to a light sheet, and a synchronizer which controls the synchronization between the laser and the camera, as you can see at the right at the top on the slide. So there are types of PIV system which are standard 2D PIV, stereo 3D PIV, micro PIV, and time resolved PIV. So the one that I will be used for the study is 2D PIV system. So the 2D PIV system is a low cost system compared to 3D, and it is easy to adjust and be maintained. Next, I will move to the methodology. So this chapter primarily help to discuss the technique utilized in the study to acquire credible results and achieve the study main objective. So the knockout 4-digit series are used in the study due its reliability and widely available data. Sorry not to mention earlier, NACA is stand for the National Advisory Committee for Aeronautics. So in this slide, I will discuss about the validation that I have made in my research to strengthen the argument to have a selection of airfoils by using the QBlade software. So as you can see on this graph, it was a comparison between the experimental, which was the result occur from the past study, and the result from the QBlade for both airfoils. So the XFLR5 codes implemented in the QBlade software generally show good agreement with the experimental data. So from the figure, the experimental plotted graph show an approximately linear increment up until angle of attacks 14.75 degree. So this experimental data trend line showed a good agreement with the data obtained from the QBlade software. So this is the purpose of the QBlade software, and it was clearly shown that it helps to analyze the airfoils before the selection and fabrication process occur. So to select an effective airfoil, it is imperative that airfoil chosen could operate in highest angle of attack before suffering a stall. So in this study, the chosen airfoil is determined by the desired operating parameters, such as low Reynolds numbers, high lift-to-drag ratio, a wide range of angle of attack, code thickness, and others. So the code length range of thickness is between 12% to 27%. Will be used throughout this experiment. So the selected airfoils will be used to perform more extensive physical experiment after being implemented and filtered by using the QBlade software. So the QBlade will be used to model and design the airfoil. So for the selection of airfoils, it starts with a large numbers of airfoils before be filtered by using the QBlade software. Then the airfoils then be shortlisted in 20 airfoils for asymmetric airfoils and 5 for symmetric airfoils based on their good LTD performance analyzed by the QBlade. So for the final stage of selection, 2 airfoils from symmetry and 2 airfoils of asymmetry have been chosen to be used in experimental in order to achieve the third objective of the study. So move forward to the PIV experimental rig and instrument. So this is the system that I will be used for the entire research for the data analysis. On the left side, show the Edu PIV system that can be found in Dynamic Lab at Block C and at the right side of the slide, you can see the image and how the PIV system works. So the video I show here is actually captured by using the handphone, and it just roughly to show the use of the PIV and how it works basically. So this is how it works. So, in this slide, I will show some of So in this slide, I will show this is the experiment configuration for hanger and connector. So this is the design that to be fabricated to use during the experiment. So in this slide, I will show some of the part during the fabrication process of the experimental rig, starting from the setup of the 3D printer, the fabrication of hanger and connector, and also the fabrication of airfoils. So this is when I fabricate the hanger and the connector, and this is when I fabricate the airfoil. So the process sometimes have a bit challenging when using the 3D printer to fabricate the experimental rig, as there are always some error during printing, such as the filament is stuck and the final product of printing not come out perfect. So after about 1 month of fabrication, here is the selected airfoils and experimental rig that I used for this study. So as you can see in this slide, this is how the setup for PIV system during experiment. So during the experiment, the light must be light off as the system must be captured in the dark place. So settle with the methodology. Now we move to the result and discussion. So this slide is about the analysis on Reynolds number in the PIV system without an airfoils. So as we can see from the previous slide, the water in the tank are not much clear. Thus, that will affect the data measurement. So based on the vector velocity image here, the localized vertex shown in the figure, which is this one, could be from the unclean fluid. So hence the collection of the data from those particles might be hampered from the fluid that is less than clean. So as evidence from here, the noise could be the reason for the imperfect data. So the Reynolds number is calculated from the analysis is 573 and 0.53, which is quite low. So this is example of how I measure and capture the particle seed. So the normalized distance from starting point, which is near from the mouth of the nozzle, and the end point is approximate 2.5 cm from the tail of airfoil. So as you can see at the right side of the slide, this is the experimental view before being processed using the PIV system. So for the symmetry, for the NACA 0015 and NACA 0027, the highest velocity recorded is 0.114 meter per second at 0 degree angle at NACA 0015, while for NACA 0027, the highest velocity you can see here is 0.007 meter per second at 20 degree angle of attack. So from the graph, it showed that once the angle of the airfoil is increased or decreased more than 0 degree, localized vortex occur in the fluid flow, which would intend making the capturing of data a challenge because the software could not correctly capture the velocity data from these located vortices. So that is the reason why the velocity of the other angles are low and undefined. So a better numerical technique should be developed to better capture those missing data. So next, we move to the NACA 2817 and NACA 6921, or known as asymmetrical airfoil. So in this slide, it's shown that the highest velocity is 0.01 meter per second at 20 degree angle of attack on NACA 2817, while the highest velocity of NACA 6921 is 0.008 meter per second at 10 degree angle of attack. So as can be analyzed from this study, the localized vertices along asymmetrical airfoils are more evident based on the figure. So at 0 degree angle, the localized vortex are starting to be developed in second point, and it becoming more pronounced when the fluid flow is moving towards the third point where the velocity is almost zero. If we take a look at a NACA 2817 over here, at higher angle of attack, the velocity increase again as the fluid flow moving to the back of air force because the vortex has been stabilized and re-emerged with undisturbed fluid flow. So we have come to the conclusion. Now, the first objective of the project, which is to carry out a selection process of a high lift to drag ratio airfoils based on the NACA 4 series using the Q-Blade software has been fully achieved. So the airfoil chosen could operate in the highest angle of attack before suffering a stall. So the second objective is an experimental rig of the PIV system was also successfully designed and fabricated. So I like to say that the experimental rig is fully functioning during the experiment, and though the localized vertices occur in some cases of the airfoils, the measured data have shown that the velocity vectors have indicate the differences in the lift to drag ratios among the airfoils. So the investigation into the characteristic of the different airfoils have been done up to certain points. So therefore, the third objective has been fulfilled. So before I end my presentation, I would like to suggest some future improvement to for this study to get a better result. So some improvement maybe can be done by using 3D PIV system so the image can be captured from the different axes. And the next one is the test methodology can be changed by using another type of airfoils. So to find airfoils that can give a high performance in different angle of attacks. So the next one is the experimental rig design can be improved. So the angle adjustment can be made easily. Last but not least, the experimental can be done by increasing the Reynolds number. So that's all from me. Thank you. That's all from me. Thank you for the examiners, Dr. Kamil and Dr. Famianyan, for your time for listening to my presentation. I wish everyone have a nice day. Thank you.